Good morning. I am Ms. Gina Klinangandi, presenting our paper Recognizing Semantic Relation in Sentence Pair using Tree-RNN and Type Dependencies, which has been co-authored with Dr. K. A. Abdul Nasir. We are from the Department of Computer Science and Engineering, National Institute of Technology, Calicut, India. It is a trivial question for humans to identify which of these sentences are similar, whereas it is challenging for a NLP system. Here we can see the pair AC and BD are similar where all other pairs are dissimilar. Our work focuses on this research problem of how to identify if the given sentence pair are similar or not. Recognizing textual similarity is a crucial step in many NLP applications, including question answering, paraphrase identification, information retrieval, machine translation evaluation, just to name a few. And linguistic knowledge was very essential in identifying many subtle relationships, which we will see shortly. In this work, we propose to use grammatical relation between words to learn better sentence representations. We got improvement in classification accuracy as well as correlation in relatedness scoring on benchmark dataset. The figure shows the ordered dependency tree of two sentences. The two trees looks exactly identical except for their edge labels. So here now the edge label of fish and following is end subject, that is nominal subject, and in the second case it is direct object, changing the meaning of the two trees just by the edge labels. So change in syntactic and semantic role of trees changes the sentence meaning. Our approach. This figure shows the generic framework for sentence modeling which we have followed. The training data consists of a set of sentence pairs, say S1 and S2, and the output is a class label or a real value depending on the task at hand. So for semantic relatedness scoring, we generate a real valued score, and for recognizing textual entailment, we generate a class label. So coming to the figure, it consists of three layers. The input embedding layer takes sentences as a list of words and also use a dependency parser to generate the type dependencies. So the input embedding layer takes both the words as well as the relations and embed them into fixed dimension vectors. So here we have used glow vectors, pre-trained glow vectors as word embeddings, and dependency type embedding is learned using an embedding layer. In the second step, we proposed a dependency type RNN which takes in this word and relations and produces a sentence vector. So in the third step, the output classification layer takes the distance between these two vectors, sentence vectors, that is the absolute distance and the dot product, and gives it to a softmax classifier. The softmax classifier predicts a probability vector which is then converted into a class label or a real valued score. So this framework was adopted from the famous work by Tai and others in 2015, and the model is trained end-to-end using mini-batch gradient descent algorithm. The training objective is to minimize the KL divergence loss between actual and the predicted probability. So coming to the proposed model, the intuition behind this model is that grammatical relations contribute equally to the sentence semantics as much as the words. So that is the novelty. Existing DT-RNNs does not take grammatical relations into consideration, but grammatical relations are equally important. That is what we emphasize in this work. A Tree-RNN that is unaware of edge labels cannot identify identical trees which have different meaning. So the solution which we put forward is that we learn a fixed dimension vectors for each type of dependency relation, and we use this vectors along with the word embeddings. So a toy example is shown here with 5 dependency relation and an embedding matrix where each row corresponds to a dependency type. So this is the proposed architecture of DT-RNN model. Every node is represented by 4 sets of neural network. Each neural network is a symbol feed-forward neural network with a single hidden layer. Input to each node is one hot vector that represents a relation of the node with its parent. A word vector, a pre-trained word vector that corresponds to the word at that node. And at every internal node, we have a list of hidden state which represents the node's child nodes. So, every node produces a hidden state which represents the sentence or the phrase rooted at that particular internal node. So, at the root of the tree, we have the sentence embedding. So, this is the mathematical equation. Please refer to the paper for details. This shows how the vectors are combined at each node. So, here you have the orange vectors which are word embeddings, and you have hidden state vectors shown in blue. The dependency embedding is the green vector which is learned using an embedding layer. The hidden state is concatenated with the dependency embedding to produce a dependencies specific hidden state. So, at every internal node, all the child nodes are summed up, and then the procedure continues. So, we evaluated our model on 2 benchmark applications. The first one, recognizing textual entailment. So, given a sentence pair, the goal is to classify it as entailment, neutral or contradiction. That is, does sentence A entail sentence B, or are the relation neutral, or does the 2 sentences contradict each other. Here the P is the predicted label and G is the ground truth. In the first example, you see there's very little overlap, still the model correctly predicts the relation as entailment. In the second example, there's again high overlap but a change in the noun. So, nobody is replaced by someone. So, the model correctly identifies this as a contradiction. In the third example, again the verb hitting is replaced by missing. Again we have a contradiction which the model correctly identifies. In the fourth example, the model is misclassifying this as entailment, though it is a contradiction. Here the change happens at the adjective. So, from this example, we understand our model is giving more importance to nouns and verbs compared to adjectives, which is expected. Then we have recognizing textual entailment classification accuracies for different types of model. In the first category, we have the recursive neural network. Second category, we have sequential LSTM, and in the third, we have tree-structured LSTM. Our model outperforms recursive neural network, all the recursive neural network, and about 2% increment in over the DT-RNN. It has comparable result with the sequential LSTM. LSTMs which are more powerful model with tree knowledge outperforms our model in this task. Then we have semantic relatedness scoring, where the goal is to generate a real valued score for each sentence pair. So, we compare the human generated score and the machine generated score and find how much correlation exists between those. Again, we have 2% improvement over the base model SDT-RNN, which is 79%. So, we got 81.16. Same is the case with Spearman correlation and mean squared error. Then coming to the learning curve, the figure shows the learning curve of our proposed type DT-RNN orange with the base model DT-RNN shown in blue. So, you can see there is a clear advantage for the proposed model over the base model. So, it is able to learn much faster than the classic model. So, to summarize our work, we introduced type dependency embedding to represent grammatical relation. We proposed Tree-RNN model that can use both words and interrelation for semantic composition. We evaluated on 2 NLP tasks and shows approximately 2% improvement in classification accuracy as well as Pearson correlation. And talking about parameters, we use much lesser parameters compared to the SDT-RNN. So, hope the talk was informative. Please feel free to revert back in case of any clarification. These are the references. Thank you.